Good afternoon, everyone, and welcome to this exciting session of Digital Vidya webinars. The topic for today's webinar is how naive Bayes algorithm works. And to lead the webinar, we have with us Akshay Sehgal, who is the General Manager for Data Science at Reliance Industries Limited. Akshay is proficient in designing, training, and deploying machine learning models. He has expertise in building new age enterprise scale data science solutions across multiple domains. I welcome you, Akshay, in this webinar session, and now over to you.
Thank you, Niharika. Hi, how's everyone doing? My name is Akshay Sehgal. I think Niharika has already given a quick introduction about me. Um, so just to elaborate a little bit, what I do with Reliance is building machine learning models, specifically to help out HR platform teams and employee services. So we do a lot of image processing, a lot of natural language processing. And the topic that I chose today was something that I think anyone can identify with, including people who are new to the domain, as well as people who are, just starting, already practicing the domain for quite a while. Because naive Bayes algorithm is one of the benchmark algorithms that you usually start off with to, have your first cut of the model classification model. Um, so Niharika, would you be able to just help me out with the poll that we talked about so that I can get
Yeah,
a
sure. Just a
rough
minute here.
understanding of.
So I am launching a poll here. Can you please fill in your relevant responses for the same?
All right, great. Let's do the second poll as well if possible. Okay, great. I think I get a rough picture of what's the audience demographics in these terms. So yeah, that's great. So what we'll begin with in this particular session is first to get a different perspective on machine learning, because I feel that that's one thing that is kind of missing. There's too many interpretations. Some of them are very technical in nature, and some of them are more involved from a very high intuitive perspective, but they lack it somewhere in terms of really understanding how to implement it from the perspective of somebody who is doing hands-on work on machine learning. So let's start with the with the first slide. um, I want to talk about machine learning from a different perspective, which is called the black box approach, right? Any open system can be represented as a black box, where you have inputs going into a model and outputs, right? uh, Specifically for mathematical models, you would kind of represent it with the function fx and some theta, which is input parameters. I'll come to that in a second. But this is what the what a black box view of a of a system looks like, right? Stimulus and response. So let's look at the first scenario. Let's assume that you know what the model is, you know what the outputs are, but you don't have any understanding of what the inputs are, right? A typical scenario might be, for example, you plan to invest money into different channels, and you need to see what your profits are. So now you understand how the model works because you know what are going to be the underlying calculations that are going to happen on those investments. You also understand what is the output that you're looking for. You're trying to either maximize your returns, or you're trying to get a minimum amount of xyz. So that's, you understand that. And what you're trying to understand is what would be the right inputs. How do I distribute my investments across these different channels, right? So typically this is, in general, this is an optimization problem. When you know the model, you know the outputs, but you're trying to figure out what would be the right inputs. The second thing that can happen is, uh, you know the inputs, you know the model, but you have no idea what the outputs are going to look like. With the same example, you know what are your input ranges that you want to invest. I can invest this much and this much and this much in these channels. I understand how the calculations are going to work, but I have no idea what's going to be my profit because the calculations are kind of complicated. So what you would end up doing is you would simulate different inputs over ranges, kind of collect samples from what is going to happen when you change the inputs, you tweak the inputs in different combinations, collect the various outputs, and then analyze the outputs in terms of, say, distributions, understanding this is going to be my average return, this is going to be roughly my deviation in my returns and the variance in my returns. And this is a simulation problem, right? You have examples of Monte Carlo simulation and so on. Just to go back to the previous slide, an optimization algorithm example would be, optimization under constraints using dynamic programming, optimization using convex methods that do convex optimization, for example, stochastic gradient descent algorithms. These are things that you would get introduced to as you get into the machine learning field, and these are very critical, very, very critical things. I'll come back to this, why they're so critical. The third scenario that can occur is that you have inputs, you have outputs, but you have no idea what the underlying model is, right? So you're trying to approximate a function f comma theta that takes in the inputs and gives the right outputs that you're looking for. This whole paradigm is what machine learning and mathematical modeling comes under, right? Now the problem is there is no direct way of in certain cases there is, but in most of the cases there is no direct way of kind of finding out what the model is, because there are way too many assumptions that you can take, right? So there is a trick to this whole problem. What you can do is you can reframe this whole problem as an optimization problem. So what you end up with is that you assume that my model is going to be like, let's say, support vector machines, which is a type of classification model that is quite popular in the industry. So let's assume that you say that I understand that my model is going to be support vector machines. I know what my inputs are going to be. I know what my outputs are going to be. What I'm trying to figure out is what would be those parameters or the optimal parameters when I input, have some computations with my inputs and give me the right outputs. So now you are back to the same input, finding the input, knowing the model, knowing the output scenario. So this is how most of the machine learning algorithms work. However, not all of them work in this way. Some of them are quite logical in their approach in terms of using overall cohort statistics. And that's where we come into our topic for today, which is naive-Bayes algorithms. So naive-Bayes algorithms first became popular in 1998. Theoretically it was already it was already there because it's based on Bayes theorem, and it's a very popular classification algorithm. But it first became popular when it was actually used and published as a paper for as a spam classifier. And in around 1998 there were a lot of the internet was booming, a lot of email services were coming up, a lot of tools were being used to classify which one is a spam and which one is a ham email. So naive Bayes is one of those algorithms that first became popular during that era. And it comes under the family of probabilistic classifiers. There are different types of classifiers. So support vector machines, for example, is a kernel-based classifier. You would have heard of an algorithm called KNN, K nearest neighbors. It's a distance-based classifier. So underlying method of how those calculations are made to really classify something come from the the class of, or the family of, classifiers. So naive Bayes at its core is essentially two things: your Bayes theorem and a naive assumption, which we'll talk about. So how I want to do this is I'll go through both of these separately. We'll get into a little bit of mathematics, but the point of that mathematics is just to understand from an intuitive sense what is happening behind the scenes, right? Uh, then after that, we'll go into the industry implementation, what usually people do when they need to implement Bayes theorem, and we'll be looking at a little bit of Python code. And then post that, we will be looking at how to implement naive Bayes from scratch using Python, which is not necessary, but it's going to kind of give you what happens, one by one, step by step inside the naive Bayes algorithm in different scenarios. So to start off with Bayes theorem, one of my favorite definitions for Bayes theorem is by a professor at MIT. What he said was that you know something about the world, and based on what you know, you set up a probability model and you write on the probabilities for all different possible outcomes. Then somebody comes and tells you some new information, such as this event has occurred, and you have to now change your beliefs, and now you have to update your probabilities. And create a new, update your probability model. And this is what Bayes theorem is all about, right? So we'll very quickly go through, a scenario where let's assume that this is a probability model that you have set up. Two events can occur independently, A and B, and there is a small chance that neither of the events occur, which is shown as 0.1, right? The probability that both A and B occur together is 0.3, 30%. The probability that only A occurs is 0.4, and the probability that only B occurs is 0.2. So this is only this area and this area, right? Now, let's say somebody comes and tells you that B has occurred, right? So essentially, all this region outside B, since B has already occurred, all this region outside B now becomes completely meaningless, right? So what you end up with is your new space under which you're setting up your probability model now turns into just the area that you're looking at under B, right? So now what happens to the older probabilities, and how do you readjust probabilities? Because the total probability of B occurring is already 1, and that's what the information was given to you. So the next state, at the next state t is equal to 1, the probability of B is now 1, and so you have to readjust the older probabilities, which were 0.3 and 0.2, to sum up to 1 essentially. So as you can see, this area is A intersection B, the probability that was out here. So now probability of B is equal to 1. So what would be the probability of A intersection B? That will be equal to probability of A intersection B divided by probability of B, which turns out to be 0.6 probability. So there is a 60% chance that A will occur now, knowing that B has occurred. And this is how we denote it, right? P, A given B. And what would be the remaining probability? That B doesn't, A does not occur, given that B has already occurred. That's simply going to be 1 minus A intersection, A given that B has occurred. So with that, you can kind of see the symmetry in that equation. Somebody can tell you that B has occurred, which was the scenario that we were talking about. Somebody can also tell you that A has occurred, which is the second scenario, and you just kind of flip the whole thing around. Using these two equations, you can kind of see that this is the common term, the A intersection B. So you can kind of replace it to get the derivation for Bayes theorem, which is the probability of A given that B has occurred is equal to the probability of B given that A will occur, multiplied by the probability of A and divided by the probability of B. Now, this is an important equation because we are going to reframe all our machine learning problems from a probabilistic standpoint as this equation. And I'll come to that in the next stage. So Bayes theorem, I think we got a general understanding of that. Now let's come to the naive assumption that we make. So now the equation that we talked about, the Bayes theorem equation, right? We can kind of rephrase our whole machine learning problem as a problem, in this format. So what you're trying to really say is, what is the probability? So let's only look at the probability on the LHS of this equation, right? What is the probability of getting a given label y when certain specific values of x1, x2, x3, and so on happen? Now, what is this? These are the different features. Essentially, this is equal to one row in your data set, right? So for let's take an example. Let's say you have you have a data set where you have multiple values for different features of a plant. For example, the sepal size, the petal size, the width of the petal, and so on. And you're trying to classify which particular plant or which particular flower does that particular those features belong to. So your x1 and x1 to xn are basically your features, the values of the features, and you're trying to understand what is the probability of this being the first class of that uh, particular particular flower or tree, a flower or plant, and so just rewriting this whole problem as a as a in terms of Bayes theorem, you kind of get a sense that the same formula is applied. So this is the probability of that particular class just happening over on the data set. This is the probability of all the different variables, and this is the probability of all the different variables having a specific value, given that this is the value of y. Now, here comes the naive assumption. The naive assumption is conditional independence, meaning that variables do not have any dependency between them, right? They are purely independent variables. So that is the the naive in naive Bayes. Once that happens, you can see what is going to be the consequence of that. Because if there are two independent events, you can write the common probability, the combined probability, joint probability of them occurring as independent probabilities, P of A and P of B, right? So what ends up happening is this probability component out here can now be divided as these the multiplication of multiple probabilities, and same with the denominator. So now what happens after that is you can just kind of rewrite the whole equation as in a slightly more formatted manner. The probability of y does not change, right? The probability of y is the overall probability of that particular class or that particular label. Now, the denominator also does not change because that is kind of the overall probability of inputs. That does not have any dependency on y or the occurrence that is there in the data set. So computationally, you can kind of remove this and kind of say that the probability of y, given that specific values of x occur, is proportional to this particular equation. And so you end up with calculating probabilities for each class. So let's say there are 3 different types of flowers that you're trying to classify. You're going to calculate the for a specific value of inputs that you have. You're going to independently calculate what is the probability of the first what is the probability of this particular series of inputs to be the first class. What is the probability of the second this series to be the second class? What is the probability of these inputs to be the third class? And then you're going to do what is called a maximum posteriori decision rule, which is simply saying that I'm going to look at the 3 probabilities that I get for all the 3 classes. And I'm going to choose the maximum one, and that's going to be my answer, right? So this kind of gives a sense of how the mathematics works. And this is going to be the last of the mathematics that we're going to talk about. We're going to get into the implementation. But before we get into the implementation, I just wanted to show this image because as a classification, if you're getting into the classification domain, it is very important to kind of get an intuitive sense of how decision boundaries are drawn, right? So now imagine that these are your data points in 2 dimensions, and you have 2 different variables, x1 and x2, and these are the classes red and blue. You're trying to classify data based on which one is red and which one is blue. Now, if you look at naive Bayes, unlike other algorithms that are shown out here, kind of has a very smooth contour when it tries to separate out. It does misclassify stuff, but it is really good at generalizing its predictions, right? It kind of captures a concentric circle problem, which is a very common problem that a large number of classifiers are not able to do, specifically linear classifiers. But you can kind of see that in an intuitive sense in 2 dimensions what my classification, my decision boundary is going to look like. And this intuition can be carried to higher dimensions, meaning this, if you have 100 variables that you're trying to do, you can kind of imagine some similar sort of a decision boundary happening in that space. So what I'll do now is I'm going to change the screen to the Jupyter notebook, and we're going to look at some basic implementation. Any questions till now?
No questions as of now, Akshay. You can still continue.
Okay, cool. I'll do that. Just give me a second. I'm just trying to figure out. Yeah, are you guys able to see my Jupyter notebook? Okay, I'll assume that you are. Let's go through a little bit of code. So naive-Bayes algorithms, in a very simple sense, you don't really need a lot of knowledge to implement it. It's quite straightforward. And we're going to very quickly implement it because I want to get to the next part of the session where we actually implement it from scratch, step by step. So let's assume that you have a data. We're going to pick a data set called iris data set, right? This iris data set, I have an example of what it looks like. Yeah, so this iris data set essentially looks like this. So it has 4 different variables. You have sepal length, you have sepal width, you have petal length and petal width. And then you have a class. This class can be 0, 1, or 2, right? So essentially what you're trying to do is based on the features, the size of different parameters that are there for the leaf and for the petal and the sepal, you're trying to classify out of 3 different classes which flower does it belong to, right? So very quick implementation. You set your x and y variables, right, which is the raw data, which includes the 4 features, and your target variables, right? So your column names are sepal length, sepal width, petal length, and petal width. The shape of the data set is 150 rows with 4 columns, and your target values are these 3 values, right? Okay, cool. So now the first thing that you would do in any general machine learning practice is you would split the data set into testing and training data sets. The reason why you do that is because your training data set should not really learn what essentially what you're trying to do is you're trying to generalize the model as much as possible, right? So if you take the complete data set and train it on the complete data set, what you end up with is the accuracy of the training data set, but you don't really know how well it will fit on new data that comes in, right? So you essentially kind of simulate that process by taking around 10 to 20% of the data set, keeping it aside, untouched. You train the model on 80% of the data set, and then you kind of see how does the model perform on the remaining data set, right? And multiple scenarios can happen in that thing. One of the scenarios is overfitting, which we'll not get into right now, but you try to see that if you're getting say 90% accuracy, does my training does my test set get 90% accuracy or around 90% accuracy as well? If it does, then you have to kind of train a model that is generalizable, and it's not going to be a model that will overfit, right? So right now I'm going to just use scikit-learn, the scikit-learn naive Bayes API that provides a particular Gaussian NB. We'll look into this Gaussian naive Bayes in more detail, later on, right after this. But you apply Gaussian naive Bayes, you train the model using a command called nb.fit, and then you score it on the test data set, and you get around 93% accuracy. A simple example is, let's say I manually put in some values for the 4 variables and I try to predict what it is. So it gives me a value of 1, saying that this is the versicolor flower. So I hope that is kind of clear to everybody, but we can kind of go through the code in more detail later on as well. Now, I want to get into a session where the part of the session where we actually understand what is happening behind the scenes, right? Now, one of the things that we talked about when we were trying to understand how naive Bayes work in general is that we talked about probabilities. Probability is basically number of occurrences divided by total possible occurrences, right? So the problem with that is that when you're talking about a continuous variable, right, a number that can be, that can, have any particular value, any numeric value, float value, you don't really get to choose counts, right? So something can occur 3 times divided by all possible times that the event can occur 10, so 3 by 10 is the probability. But if the value of the variable is continuous, you can't really do that. That's where you go with a transformation which is assuming that you are working with a Gaussian distribution, right? Now, a Gaussian distribution, everybody knows the bell curve, right? So what you're trying to essentially do is you're trying to estimate that if I have, so I have, a particular variable that has like values ranging from 1 to 10, right? And these values, occur in my data set with different value, different particular values. Now, what I'm trying to understand is if I tell you that a value of 7 has occurred, then what is the probability of that value of 7 with respect to the data that I'm seeing, right? So the formula for that essentially is this, right? If you use, we're not going to get in the formula, but this is the formula for bell curve essentially. What it returns instead is that if you get a particular value 10 and you know what the different samples are from that particular feature, you can kind of estimate that what is the probability of 10, and that is what we require in our previous equation, if you remember, right? So the previous equation needs you to calculate the probability of overall probability of y and the probability of each feature with respect to that particular y occurring, product of that, right? So there are, for example, n number of features. In this case, there are 4 features. So what you're trying to do is you're trying to calculate the probability of the first feature uh, given the value that is coming for the first feature given a particular y occurring. So you need these terms, right? P, X, I, Y, right? And this I'll come to later on. Uh, so now we're just trying to implement the formula out here, right? And we'll come to this chart in a second. But what you essentially see out here is the raw data set. You have your unique different priors. So this kind of tells you what is the overall probability of y, right? And overall probabilities of labels in the data set are also known as priors, right? These are the prior probabilities that you have for the data set. So class, so essentially what you do is you know that there are 150 rows, right? So what you're trying to do is out of those 150 rows, how many of them have the label 0, how many of them have the label 1, how many of them have the label 2. In this particular data set, all of them are equal, 50-50 each. So the probability is 0.33, right? So you have this particular list of priors, right? So this is your PY. Now, you have the class-wise means. So you basically group by the complete data set and you take the mean of each variable with respect to that particular class. So what is the, if the class is 0, what is the average of sepal length? What is the average of sepal width? What is the average of petal length, and so on, right? So you calculate these because this is necessary in our this formula. We are trying to find the mean of that of each variable. What you also require is a standard deviation, right? For this, in order for you to calculate, and that's used in 2 places out here. So what you end up with is the second thing as well. The same formula, group by, but you're trying to find the standard deviation, right? Now think of this whole problem as, you take in a particular value, you take the mean of that particular value with the for that particular label, you put it into that, you take the standard deviation and you calculate one single value, right? Now computationally you can do it very simply with a a large loop happening for each different value that is there in the data set, in your input, right? But what happens in the background is when you're actually implementing it with Python or maybe any other language, you end up using a lot of matrix computations. So this is what I wanted to kind of simulate with this particular diagram. So we looked at three different things, right? We looked at the table with the complete class-wise means. We looked at the table with the complete class-wise standard deviations. So both of these are 3 cross 4 and 3 cross 4 matrices. So in this particular case, these are your class-wise mean. This is your class-wise standard deviation, right? So 4 different variables, 3 different labels, right? How do you compute the values for all the PIXI in one go? What you do is you have your input feature. So let's say I'm setting the value to something like this. This is my input feature, right? The feature vector. So I'm saying that, I'm trying to calculate what is going to be the label or which flower does this belong to, right? So this is 4 different values for x1, right? This is my input feature vector. Now I broadcast this input feature vector into for each of these 3 labels, and then all I do is I put them into a function, a vectorized function that computes computes it element wise. So it takes the first value for each, does some computation and returns the first value, takes the second value for each, returns the second value, and so on, right? So what you end up with is a table that gives you the probability of xi given y for each different label for each class, right? So the function is written out here, right? So this is a standard function. I put in a value of x, I put in a value of mean, and I put in a value of standard deviation, and it just computes what is the probability using the Gaussian distribution, the same formula that we looked above. Then I can take this particular function and I can put it into numpy.vectorize. So what this essentially does is that instead of expecting single numeric values, this function is going to expect uh, matrices of the same dimensionality, right? And it's going to return a matrix as an output. So it's going to do all the computations in one go together, right? In a vectorized form. So now once you have this particular table, the next thing that we talked about in the equation was that we want to calculate the product of for a given y, we want to calculate the product of all the different features with respect to y, the probabilities of product of all different features, right? So what you end up doing is for label 0, you want the multiplication of the value that sits here, in the first row. So all you do is a row-wise product, right? So you end up with a matrix that has 3 labels and one particular product. Now there was a py that you had to multiply at the start, right? And we calculated the py, the probability of y out here. So this was the priors, right? The probability of each label occurring in the data set, which was 0.3, right? So you take that for each variable, you multiply that with this, and so you end up with a particular table. You end up with a particular matrix, which is a 3 cross 1 matrix that contains what is the probability of given the input feature vector that I'm trying to predict, what is the probability of label 1, 0, 1, and 2. And then all you do is an argmax, which is basically the same thing that we talked about. Just find out which one is the maximum among the 3, and then return that particular value, right? So a small example of this out here from the implementation perspective, we calculated the class-wise means, we calculated the class-wise standard deviations, we calculated the priors, and then we created a function that would compute the probability density function, which is your Gaussian probability function. We vectorized that so that it can take matrices as inputs. Then all we did was we had our this is just setting them to the right sizes. When you apply the vectorized function with the matrix of the sample that you have, the matrix of the mean, and the matrix of the standard deviation, you end up with a matrix like this, right? So each of these is something that you need to multiply row wise. So now when you do a row wise product, on axis 1, which is this axis, you end up with 3 different values. These 3 values represent the product of probabilities, this particular matrix, right? So now the next step is to multiply that product with their priors, which you calculated the 0.33, 0.33, so on. When you multiply them element wise, you get a matrix that contains this. And these are the 3 different probabilities that you predict with respect to label 0, label 1, and label 2. Then all you do is take an argmax, and since this one is the maximum out of them, it returns a value of 0, which means that this particular sample that you input is actually class 0, which is setosa, right? So this is how you would implement a Gaussian naive Bayes classifier, right? This is one of the classifiers that is available to you when you are working with scikit-learn and implementing naive Bayes, right? Now, what do you do with the different other different classifiers, right? One of the other major classifiers that is used quite often is something called multinomial classifier, right? Now, this is a very popular classifier because this is quite useful when you're trying to work with text data. And we're going to see an example of how to implement this. But there are different classifiers that you have a Bernoulli classifier, you have multiple other classifiers. I'm going to only talk about 2 of the classifiers. This one being the most prominent one, the Gaussian classifier. The second one being the multinomial classifier. Now, let's take another example. Let's say I'm trying to find positive and negative reviews, right? I have text data which contains short sentences like this, and you have a label in front of them saying, this is positive, this is negative, and so on. Let's assume that you have a very large corpus of such stuff, but we're going to look at a very small toy example of it so that we can see what exactly is happening. Now, the formula for what you're trying to calculate, which is this still remains the same, right? But when we were working with continuous variables, the only difference was the assumption that the continuous variables are distributed, as a Gaussian distribution. That is why the method that we use for calculating probability was slightly different, right? We use the equation for the bell curve essentially to calculate the probabilities. In this case, we are just talking about occurrences of certain words, right? Whether a type of word occurs or not kind of contributes to some extent to whether the sentence is positive or negative in terms of its review, right? So it doesn't really require a formula like that. You can kind of get away with how many times that word occurs with respect to a particular label, right? And use that frequency analysis to kind of calculate the probabilities, right? Now, when you try doing that, you end up with a very simple problem, which is the product of probabilities, right? So we'll get back to this particular equation now. You're trying to calculate the product of probabilities. So let's say this word xi is a word called, let's say bad, for example. Now, you're trying to understand whether, how many times does the word bad occur in this particular sentence with respect to, a particular class, say positive review or negative review, right? What happens if the word does not come in the sentence? So the number of occurrences of that particular word becomes 0. What you end up with is one of the elements in this product of probabilities becomes 0, and product of that would mean that you get a your value of 0 across the equation, and that is something that we don't really want, right? We want a probability. We want to say that there is very little probability of this particular if even if the bad does not occur, the probability should not get to 0. It should just reduce in number. So a mathematical notion of Laplace smoothing comes out here. So we'll not get into Laplace smoothing and what it is about. So it's also called Lidstone smoothing, but you can kind of read about this slightly later. It's nothing to do with the model. It's just an approximation that we take so that we don't get 0 values for probability, right? So this is your thing that you're trying to calculate, the probability of xi given y. all you do is you add some number on the numerator and you add some number in the denominator. That's it. So that you never get a zero numerator and a zero denominator, even if the values out here are zero, right? So you never run into a situation where where you get a zero probability. Your numbers become very, very small, but the probability still is non-zero. So you can go ahead with computation, and that is the only approximation that we make in this particular case. So let's try to implement this. So for this, I'll use something known as the count vectorizer. I think most of you, if you have worked with data sets, you would understand what bag of words approach is, which is basically looking at each word that occurs as a part of a vocabulary and using that as a feature, right? So I'll show you how does that look like. So all the different words that occur in the corpus that we had. So we had 1, 2, 3, 4, 5, 6, 6 different sentences and their corresponding 6 labels. When I fit a count vectorizer onto it, essentially what I end up with is all the different words that can occur for each sentence and whether they occur or not, right? So in this particular sentence, you can see that the word with, quite, it, happy, these occur. So there is a 1, otherwise it's a 0, right? And the class for this particular variable is positive, right? So this is the bag of words representation of this particular sentence with respect to a vocabulary that it automatically picked up from the different words that occurred in this, right? So if I want to train a model, I'm going to have all these as features. So I have a vocabulary size of 14. So I have 14 different features that I will be inputting with zeros or ones to my model with a y variable of positive or negative, right? Now, all you're trying to do is calculate, again, the same thing. So like we had calculated in the previous step, what are my priors? What is my overall probability for my y variables? You get 3 different, out there were 3 different labels. So you had 0.3, 0.3, 0.3 probability. Out here, you have 2 different variables. And in this particular data set, they're equally distributed. 3 of them are positive and 3 of them are negative. So you end up with a, prior probability of 0.5, 0.5 for each, right? Then what you're trying to calculate is what is the total number of occurrences of a given word with respect to positive or sorry, 0 represents negative and 1 represents positive. So bad, the word bad in total occurs twice with negative reviews and occurs 0 times with positive reviews, while happy occurs twice with the positive reviews and 0 times with the negative reviews. So this table kind of represents that, right? Then you are trying to calculate how many times in total does my occurrences happen, with a particular label, right? So you're basically taking the sum of row-wise sum of all of this, right? Essentially, coming back to what you're trying to do is you're trying to calculate these 2 values, and then thus input some alpha and some alpha d, which I'll come to later on, to calculate the probabilities of xi, so that you can put it into the initial equation to calculate your overall probability. So this is what this function basically does. The reason why there is a try and except out here is because in certain cases the denominator value is going to cause some problems, right? So essentially what this does is it takes in the whole value, and in certain cases it returns a 0 value if the denominator happen, but we don't really have to worry about this. This computation is just a representative. The computation happens in the background. So you essentially for the different for the sentence that we are taking in this particular case, let's say this is our sentence, happy with the product. This is what we are trying to predict. Essentially what it is going to do is it's going to take the how many times does happy occur with respect to positive and with respect to negative, calculate this particular equation independently for each word. Then it's going to take a product of all the different thetas, right, over the axis 0, which is column which is row wise. So you're going to get the total probabilities out here, and the same thing that you did before was you multiply it with your your priors, which is 0.5, 0.5 each. You multiply these two numbers and you take an argmax. So what you end up getting for this particular sample, happy with the product, you end up getting that this is a positive label, right? 0 represented a negative label. So now you can kind of read a lot more about all of this, from some of the links. If you want to just kind of take a capture of screen capture of this, you can kind of go to some of these links and kind of read more about how does the mathematics and the implementation of naive Bayes works. But in a sense, naive Bayes is one of the few algorithms, and I would really want to stress on this diagram if you really want to understand intuitively what is happening. Naive Bayes kind of computes cohort statistics from the data set, uses those cohort statistics to calculate feature probabilities to occur given a particular input space, given a particular input feature vector, and then multiplying those probabilities together to the priors, which is the initial distribution itself. So a label could be occurring 90% of the time, and you would want to multiply that 90% to the product of probabilities that you have, while the second label could be just 10% of the time you would want to product that, right? So you multiply the product of your condition probabilities for the different values that you have against all features to the priors, and then get a probability independently for each label to occur, and you just choose the maximum of that, and that becomes a prediction. So in a sense, that's what naive Bayes is about. I think the takeaways that you have from here is we can look at machine learning as a as a probabilistic from a probabilistic standpoint by reframing the problem as what is the probability of y occurring given a set of features to occur in a certain manner. You can use naive Bayes to frame that whole problem as a probabilistic problem, and then you can use a naive assumption to kind of state that there is no dependency or relationship between the different features. So that makes your computation a little easy, and all you end up with is independent independent probabilities that you need to product together with prior probabilities. This is the cohort statistic that you have, and find the individual predictions for each label, and then choose which label is your maximum. And that in a sense kind of covers up exactly how naive Bayes works, both in the setting of continuous variables where we assume that our variables are distributed normally, as well as in a situation where you have text data, and you can kind of calculate how many occurrences are there, but have to assume a slightly different equation, because you can end up computationally getting 0 probabilities, right? So yeah, I think that's it from my side. I would like to take any questions if there are any.
Thank you so much, Akshay. It was indeed a very valuable session. This is for the attendees. You can please ask your questions, and by the time you do that, I'm launching a poll. Kindly put in your relevant choices. Akshay, we have a question from Gaurav. Gaurav says, are all the probabilities known beforehand?
Which probabilities are you talking about? Are you talking about the conditional probabilities, or are you talking about the py? Are you talking about pxiy or py? Okay, I'll just answer both of them. Sorry, I'll just answer both of them. So py, obviously, so all of this has to come out from the data set that you have, right? The data set has information about what all different things occur and against what variables. So you, like I said before, this is a scenario where you have your x's and you have your y, right? So what you're trying to do is, if you're trying to calculate the probability py, all you are saying is how many times in my whole data set does different labels occur. So for the first case, we knew that there are 3 different labels. So I just look at how many times the label is 0, how many times the label is 1, and how many times the label is 2 in my data set, right? Because that is the only information I have about that. I have about that. I have about the system, right? Those are my samples that I've taken from observations that I've taken from the system, right? So py is that, but pxiy essentially is again coming from this particular scenario, but you have to make some assumptions, right? If you have a continuous variable, you have to kind of assume that since I know that my complete column, so let's look at one second. Are you guys able to see? Oops.
Yes,
Uh,
Akshay.
would you be able to just give me access to share my screen again, probably?
Sure.
Right. So let's assume that this is your data set, just 5 rows, right? So now I know that the values in this particular column range from something like 0.47 to 0.46 to 51, right? So now I know what will be the mean of these 5 values. I know what will be the standard deviation of these 5 values. And let's say I give you a new value, say 4.85, right? And I ask you what is the probability of 4.85 to occur in this particular setting, right? That's where you assume that your data set is normally distributed, and you use this formula where you put in 4.85 out here, you put in the mean that you calculated out of this, you put in the standard deviation that you calculated again from that, and you get a probability value saying that, hey, this is roughly the probability of 4.85 to occur in this particular setting. Does that answer your question?
The next question is from Mr. Ghosh. He says, in Gaussian classifier, we
Mhm.
used an example where priors were equal. Hence,
Yes,
classes were equally distributed. In a
yes.
rare class scenario, will this Bayesian classifier be affected?
It will. And that is one of the core problems that you get when you're doing something like when you're working with something like anomaly detection. There are quite different methods that you use. In fact, this is a problem that will occur pretty much in any algorithm. If you have one class that has way too much data available, you have a lot of observations available from that particular class. Let's say 99% of the observations come from class 1 and just 1% come from the class 2. You're going to end up having very clearly out here that is a problem, right? Because you've gone through the equations. But if you go through all the other different algorithm classification algorithm, this same problem is going to occur. Pretty much no algorithm is safe from this particular problem, right? In a sense, uh, this is a common problem across, and there are multiple ways of handling it. But I think we'll not get into that. But yeah, there are different ways of working with very high class imbalance.
We have another question from Mr. Ghosh. He says, what kind of classification problems in
Hmm.
Bayesian algorithm useful, and is there any situations when it is not?
Okay. Uh, so think of so you remember when we had looked at the whole scenario where we just translated the whole machine learning problem into the Bayesian equation, right? So this is a very general equation. What this means is any problem where you have a list of x1 to xn features and you have labels y, you can kind of reframe that whole problem as an naive-Bayes algorithm. So there are pretty much no classification algorithms where you can say that naive-Bayes algorithm will not work. Uh, but since there is something in our industry we call as the no free lunch theorem, right? You have to really implement it and understand. Now, to your question, where all it will work and where all it will not work, we can come to this diagram that I had shown before, right? So this the part where if you remember that diagram that we had seen in the slide, which had all the different classifiers. Let me see if I can go back to that diagram. Just a sec. Okay. Right. Okay. So to get an understanding of where all can it work and where all it can't work, right? Uh, this is something that you have to kind of, play around with a little when you're trying to work with machine learning algorithms, because you don't really know the underlying structure of data that you're trying to classify, specifically because it's not never going to be in 2 dimensions, right? You can use some techniques such as principal component analysis for dimensionality reduction, or you can use TSNE for dimensionality reduction and get a sense of how things are distributed. But in more often you will never really understand what's the distribution, but you can still kind of see where all it fits, right? So in a problem where you require very high polynomial, a very high polynomial fit, right, you would be able to see. So let's assume, let's take this for example. Yeah, this for example, right? So you see how the decision boundary really curves around to make sure that the data fits, right? This is not something that naive Bayes is really good at, right? It'll generalize really well. It'll kind of give you a a space between what is red and what is blue, but it's not going to really do that. But for some algorithms, if you see the concentric circle problem, right? Uh, Data is surrounded by another type of data set. Linear algorithms are trying to just cut the whole space, and they kind of fail really bad at it. Naive Bayes doesn't have that much of a problem handling something like that. So these are type of situations where it will work well. Practically speaking, I would really suggest that whenever you're trying to solve a classification problem, start with an algorithm like naive Bayes, like nearest KNN, and maybe decision trees or random forest. Try these 3 different things because they belong to different categories, right? So your SVMs come as kernel-based methods. Your naive Bayes belongs to probabilistic classifiers. You have nearest neighbors KNN, which belongs to distance-based classifiers. You have random forest, which belongs to tree-based methods, decision tree-based methods. You can even try a very basic neural network, which is a a generalized functional approximator. So you can try one of each and see what sort of accuracies and what sort of validation accuracy and training accuracy you get, and kind of decide what can be the underlying structure of the data set. But I would highly recommend naive Bayes to be one of those algorithms to start off with, right? So there is nothing stopping you from doing that. Yeah. Next question, please.
So I think we are done with the questions.
Cool.
Again, thank you so much for leading the webinar for us. It was great having you here, and thank you everyone for being such a wonderful audience. Lastly, I would like to launch a poll for you to share your experience with Digital Vidya and for today's webinar session.
All right. Thank you so much. Thank you so much, guys. You can kind of connect with me on LinkedIn if you have any further questions. Yeah. All right.
So in case if you have missed any part of the session or if you have joined late, you don't have to worry about it. We will share the recording of the video with you over an email by tomorrow or max by Friday. Once again, thank you so much, everyone. Thank you, Akshay. Thank you so much.
Take care. Bye.